Imagine a very strange place, a country where everything was flat, and that you, inhabiting this strange country, creatively named Flatland, are a square. You're aware of two types of movement, forward and backward and side to side, but you have absolutely no conception of moving up or down. Every one of Flatland's inhabitants, ranging from lines to triangles to squares to many-sided polygons, goes about their two-dimensional business and cares not for the third kind of direction. Well, everyone but the mathematicians, who try to no avail to describe this mystical third dimension to everyone else. You begin to think about a world with only one dimension, lineland. Instead of lines and shapes living on a plane, there could be points or line segments living on a line. You imagine visiting this world, and how to them you'd appear only as a line segment as you intersect their lineland. You're then visited by a sphere, only you wouldn't be able to understand what a sphere is. You only see it as an expanding, then shrinking circle. To ease your comprehension, the sphere bumps you out of Flatland and into Spaceland, where you, from a new vantage point, above, can look down on your flat fellows. Inspired by this revelation, you begin to imagine a fourth dimension, where, like the third to the second, there existed a new direction at right angles to all of forward, backward, side to side, and up and down. This is the world imagined by Edwin A. Abbott in his 1884 novella Flatland, a Romance of Many Dimensions, where he imagined how such a world would react to a visit from another dimension. We live in Abbott's Spaceland, where we can interact with and live our lives within a three-dimensional world. But what really constitutes living in the third dimension? In other words, how do you define and differentiate between dimensions? Let's start off with what an apt definition would even be. I say a good definition for the word should agree with what dimension we would typically assign to particular objects, like a point being zero-dimensional, a line one-dimensional, a square 2 dimensions, and a cube 3. You should also extend its meaning to dealing with arbitrary objects in such a way that it's satisfactorily general, simple, and helpful when it comes to other areas of math. The most common notion of dimension comes from the idea of coordinates, and specifically, that the dimension of a space is equal to the max number of coordinate values required to define a specific point in that space. What these coordinates actually constitute can vary. Think about how both the Cartesian xy and the polar angle and radius coordinate systems can be used to define every single point in 2 dimensions, and how latitude and longitude can define every point on a sphere's surface. Add one more coordinate to each, and we can define the typical 3 dimensions either through Cartesian coordinates, or cylindrically, or even spherically through 2 angles and a radius. An interesting nuance in this definition of dimension appears when we think intuitively about what separates objects of different dimensions: size. I think that for most of you watching, the fact that a cube is quantitatively more than a square is too obvious to even think about, although actually this isn't the case. In the late 19th century, Georg Cantor devised set theory and said that 2 sets of, for example, points are equal if there's a one-to-one correspondence between their elements. He then showed that a straight line segment, a square, and a cube do in fact contain equally many points. It's due to this fact that in 1890, Giuseppe Peano discovered the Peano curve, a curve that at its limit can fill a 2-dimensional surface. Mathematicians refer to a curve as simply the 2D path traced by a moving point, which means that it doesn't actually have to be smooth. In fact, this specific curve has the interesting property of being continuous everywhere, but nowhere differentiable. These kinds of space-filling curves, therefore, are able to map between 1D and 2D space, so that 2 points close together in 1D space are also close to each other after being mapped to 2D. The one thing that does separate these 2 dimensions is the fact that the converse isn't always true. It can't always be true. This is an apt transition to another interpretation of dimension, fractal dimensions, which is also a measure of the complexity of an object, which I'll get to. To define the fractal dimension of an object, you just need to ask how it scales. When you double the side length of a line segment, the resulting segment is obviously 2 times as big. When you double the side length of a square, on the other hand, the resulting square is 4 times as big, or is equal to 4 times the original square. The cube then scales to become 8 times as big, and following this pattern, some 4-dimensional object should scale to become 16 times bigger. Extrapolating, it seems to be the case that when the side length of an object is scaled by some value, such as being doubled, its size, or what's called measure, is scaled by that number raised to the power of that object's dimension. Conversely, this gives us the power to find the fractal dimension of considerably more complicated objects. If we take a variant of the space-filling Peano curve from before, for example, where the middle line of the curve is erased, we get a self-similar fractal. Self-similar meaning if we zoom in close enough, we get infinitely more copies of it. This is, at its limit, called the Sierpinski carpet. If we then scale its side length by 3, we get a similar shape with 8 times the measure. Therefore, it can be said that its dimension is log base 3 of 8, or roughly 1.89. It's 1.89 dimensional. In fact, that's how fractals are defined. They're shapes which have a non-integer dimension, generally greater than earlier, strictly integer dimensions. This is why interpreting fractals like their Sierpinski carpet through the lens of having either the length of a curve or the area of some shape feels so off. When you measure it, you find it has some infinite length, but 0 area. It's more complex than the first, but less so than the next. The most famous allegory in literature in general is that of Plato in the cave. Through Socrates, Plato asks us to imagine a group of prisoners chained in a cave from childhood, such that they cannot see themselves, each other, or anything but the wall in front of them. On that wall, there are shadows of objects that pass behind them, illuminated by a fire. These shadows are the entirety of the prisoner's perception of reality. One day, a prisoner is freed and is brought to the surface. They are blinded by the light of the surface, yet are amazed by the more genuine reality it offers. After their eyes have adjusted, when they return to the cave to share the news with their fellow prisoners, it would be too dark for them to see. Seeing the escapees' seeming blindness, the prisoners refuse to leave. This was an allegory for the philosopher's perception of Plato's forms, and can be applied to the mathematician over in the square in the story of Flatland. Even after having seen the third dimension, Spaceland, the square cannot convince others of its existence. Like the prisoners of this allegory, we are unable to perceive of 3 dimensions of reality. We cannot even conceive of the true appearance of a 4th dimension, and we must rely on visualizations of the 3-dimensional shadows cast by objects of dimension 4. The most famous of these is the shadow of the Tesseract, a 4D cube. All visualizations of this shape are dependent on analogs of a normal cube. So, like a shadow of the cube is the result of connecting the vertices of 2 squares. The shadow of a tesseract is the result of connecting the vertices of 2 other cubes, where the most common representation is where one cube is inside of the other. Similarly, like the square has 4 sides and the cube has 6 faces, the tesseract has 8 cubical cells, which, as you see, are slightly warped in its shadow, but can be seen when unfolding it into its 3-dimensional cross-like net, just like with the cube. Thinking about 4 dimensions isn't just a mathematical playing around. In fact, one of the best models for reality is Einstein's theories of relativity, both special and general, which incorporate as a key concept the fact that the universe is 4-dimensional. Einstein, or rather his teacher Hermann Minkowski, merged the ideas of space and time, such that you need 4 coordinates, x, y, z, and t, to describe your position in space-time. 2 of the most important things to remember about space-time is that 1. All objects move through it at exactly c, the speed of light, and that 2. These objects must move in a straight line, unless acted upon by a force. We, who move relative to one another at negligible speeds through space, must therefore experience time rather uniformly to be passing at c. However, imagine if you were moving at half the speed of light relative to some observer. We can draw a right triangle through space-time to see that you should be moving through time relative to the observer at the square root of 3/2 times c, or around 0.866 times as fast as them. You are therefore experiencing time slower than an observer. In general relativity, which tries to describe gravity, space-time is also, more so, heavily utilized. First, imagine you're a creature that lives on the surface of a sphere. Wait. You set out in a straight line or along a geodesic, and find that you end up right where you started. This is evidence of your world being curved. Similarly, imagine you stand on the equator and set off to the North Pole, then turned 90 degrees left, went the same distance as before, turned 90 degrees again, and continued forward. You will return back home having traced an impossible triangle whose angles sum to turn 70, more than 180. Similar to how moving on a curved surface gives you strange trajectories, moving through curved space-time, which we do at the constant speed of light, causes the phenomenon of gravity. But what causes space-time to be curved? Well, for some reason or another, objects with mass or energy take up space in space-time and push it away from itself. So imagine you're moving through space-time at the same speed c as some massive object, like the Earth. You must be moving in a straight line in a trajectory originally parallel to the object, Earth. But due to the fact that space-time curves around it, you're actually on a course set to collide with Earth, experienced by you as its gravitational pull. We live in a world of 3 spatial dimensions and a 4th dimension, time, through which we are pushed inexorably forward. We, ourselves, exist in this world and take up all kinds of dimensions. The blood vessels in our eyes are fractal in nature, with a dimension of about 1.7, as are the surface of our brains with a dimension 2.8, and the lining of our lungs with dimension 2.97. Our memories are the path through time, starting soon after birth and ending when we die. Our path out of our beds to the kitchen, to the bathroom, to the door, through our lives, take up much of the left, right, and forward backward parts of the world, with a little variation in altitude. Imagine your life as a flipbook, where each page is a consecutive moment in time. As you go through the flipbook, you trace each point in your life, and in each page is the full extent of your universe. Though you can only imagine this book having 3 dimensions, 2 spatial and 1 through time, it could be said that if you were to compile the fully 4-dimensional object that encapsulates all states of your life, it would be the best thing possible to have to be able to describe you. And in such a way, it can be said that you are a 4-dimensional being. Thanks for watching, and tune in for next time.